Hello friends, in this video we shall learn Lagrange's mean value theorem. Welcome to Dr. Patil's Mathematics Academy. Please subscribe the channel if you have not subscribed yet and press bell icon for getting updates of the channel. What is Lagrange's mean value theorem? The statement of Lagrange's mean value theorem is like this. Let f be continuous function in closed interval ab. Let f be continuous function in closed interval ab and derivable in open interval ab. Then there exists at least one point C in ab such that fb minus fa divided by b minus a equal to f dash c. This is the statement of Lagrange's mean value theorem. See again. Let f be a continuous function in closed interval ab and it is a derivable in open interval ab. Then there exists at least one point C in ab such that f of b minus f of a divided by b minus a equal to f dash c. We shall prove this theorem. For that, we shall write phi of x equal to f of x plus x into a. For any x belongs to closed interval ab. We shall define the function like this. Phi x equal to fx plus x into a. Phi x equal to fx plus x into a. Since f and x are continuous in closed interval ab and derivable in open interval ab, we have phi is also continuous in closed interval ab and derivable in open interval ab, because we know that sum of two continuous function is a continuous function and sum of two derivable function is again derivable function. That's why phi is a continuous function in closed interval ab and phi is derivable in open interval ab. Now choose the unknown constant a such that we shall try to find out unknown constant a. Suppose that phi of b equal to phi of a. We suppose phi of b equal to phi of a, then we will get f of b plus b into a equal to f of a plus a into a. From this, we can write that f of b minus f of a equal to b minus a into minus a. Thus, phi satisfies all the three conditions of Rolle's theorem. Third condition, phi of b equal to phi of a is assumed. And all the conditions of Rolle's theorems are satisfied. Therefore, by Rolle's theorem, there must exist a number c in open interval ab such that phi dash c equal to 0. What is phi dash c? Phi dash c equal to f dash c plus a. Therefore, f dash c plus a equal to 0. Therefore, we will get f dash c equal to minus a. From 1, we know that minus a equal to f of b minus f of a divided by b minus a. Therefore, we will get f dash c equal to f of b minus f of a divided by b minus a. This completes the proof of Lagrange's mean value theorem. What we had done? We had taken phi of x equal to f of x plus x into a. Now, phi satisfies two conditions, as f satisfies two conditions and x is also satisfies two conditions, continuity and derivability. Therefore, phi is also continuous in closed interval ab and derivable in open interval ab. Now, we shall assume third condition that phi of b equal to phi of a. If this condition is assumed, then we can obtain a from that, and all the three conditions of Rolle's theorem are satisfied by the function phi. Therefore, there must exist a point c such that phi dash c equal to 0 and phi dash c is nothing but f dash c plus a. That's why f dash c equal to minus a, and therefore f dash c equal to f of b minus f of a divided by b minus a. Now, alternate form of Lagrange's mean value theorem. If we put b equal to a plus h, then in Lagrange's mean value theorem, what happens? F of a plus h minus f of a divided by a plus h minus a equal to f dash c. C is what? A plus theta h. Therefore, we get f of a plus h minus f of A divided by H equal to f dash A plus theta H. C equal to A plus theta H. Theta is lying between 0 to 1. A plus f of A plus H equal to f of A plus H into f dash of A plus theta H. Theta lies between 0 to 1. Now from this we shall write some notes. Lagrange's mean value theorem is the generalization of Rolle's theorem. In the special case, when f of b equal to f of a, then Lagrange's mean value theorem reduces to Rolle's theorem. Second note, geometrically, Lagrange's mean value theorem states that the tangent to the curve at D is a parallel to the chord AB. See this figure? The tangent at D is a parallel to the chord AB. This is the geometrical interpretation of the Lagrange's mean value theorem. Now, geometrical interpretation. Let A and B be the 2 points on the curve y equal to fx, corresponding to x equal to A and x equal to B, so that point A becomes A f of A, the coordinates of point A are A f of A, and coordinates of point B are B f of B. Therefore, the slope of the chord AB is, what is the slope of the chord? F of B minus f of A divided by B minus A, because slope of the line passing through the 2 points x1 y1 and x2 y2 is y2 minus y1 divided by x2 minus x1. This is the slope of the line passing through the 2 points. By using that form, we get slope of the chord AB as fb minus fa divided by b minus a. But fb minus fa divided by b minus a equal to f dash c by Lagrange's mean value theorem. Therefore, slope of the chord AB equal to slope of the tangent to the curve y equal to fx at the point x equal to c. Hence, the Lagrange's mean value theorem asserts that if the curve AB has a tangent at each of its points, then there exists at least one point C on this curve AB where the tangent is parallel to the chord AB. Third notice, the average rate of change of f over the interval AB given by f of b minus f of a divided by b minus a is equal to f dash c, which is the actual rate of change of f at some point of the interval AB. Fourth note, using Lagrange's mean value theorem, approximate solution of the equation fx equal to 0 can be obtained by Newton's method as follows. For finding approximate solution of the equation fx equal to 0, we shall suppose a plus h is a exact or actual root of the equation fx equal to 0, so that we get f of a plus h equal to 0. But f of a plus h equal to f of a plus h into f of a plus theta h, where theta lies between 0 to 1. Therefore, h is approximately equal to minus f of a divided by f dash of a. h equal to f of minus f of a divided by f dash of a. Thus, starting at a guess value a, h correction can be calculated approximately. By iteration, a better root can be obtained. We shall use this method in solving fx equal to 0. Fifth note, if capital M star and small m star are the maximum and minimum value of f dash x equal to f dash x, if capital M star and small m star are the maximum and minimum of f dash x in A to B, then m star b minus a less than fb minus fa is less than b minus a into capital M star. Sixth note, application of LMV theorem for sign of derivative. Let fx satisfy the conditions of Lagrange's mean value theorem in closed interval AB and x1, x2 be any 2 points of AB such that x1 less than x2. Then, applying Lagrange's mean value theorem in x1, x2, there exists a number c in x1, x2 such that f of x2 minus f of x1 is equal to x2 minus x1 into f dash c. If f dash x equal to 0 for every x in x1, x2, then f of x2 minus f of x1 equal to 0. That implies that f of x2 equal to f of x1 equal to some constant value. So f is a constant function in x1, x2. If f dash x equal to 0, then f is a constant function. Second, if f dash x is greater than 0, then it shows that f of x2 minus f of x1 is greater than 0. That is, f of x2 is greater than f of x1, since x1 minus x2 is greater than 0. So, f is a strictly increasing function. If f dash x is greater than 0, then f is strictly increasing function. And if f dash x is less than 0, then in similar fashion, f of x2 minus f of x1 is less than 0. That is, f of x2 is less than f of x1. Then f is a strictly decreasing function. Thus, if f dash x equal to 0, the function is a constant function. If f dash x is greater than 0, then function is strictly increasing. And if f dash x is less than 0, then the function is strictly decreasing. Now, we shall try to solve some examples. Our first example is verify the Lagrange mean value theorem. For the function fx equal to x square in interval 1, 5. We know that fx equal to x square, this is a polynomial function. Therefore, f is a continuous everywhere. Therefore, f is continuous in open interval, in closed interval 2, 3. And f is a differentiable because x square has a derivative 2x. Therefore, fx is a differentiable in open interval 2, 3. So, by Lagrange's mean value theorem, f of b minus f of a divided by b minus a equal to f dash c for some c in AB. Here, f of 5 is nothing but 5 square. F of 5 equal to 5 square. 5 square equal to 25. And f of 1 equal to 1 square, therefore it is 1. F of 1 equal to 1 square, therefore it is 1. Therefore, f of 5 equal to 25, f of 1 equal to 1, and f dash x is nothing but derivative of x square, that is 2x. Therefore, f of 5 minus f of 1 divided by 5 minus 1 equal to 2c. Therefore, 25 minus 1 divided by 5 minus 1 equal to 2c. And hence, we will get c equal to 3. And 3 lies between 1 to 5. C lies in the interval 1, 5. Therefore, Lagrange's mean value theorem is verified. Second example, f of x equal to x raised to 2 by 3 in the interval minus 1 to 1. The LMV theorem is not applicable here because f is not differentiable at x equal to 0, which belongs to minus 1 to plus 1. How f is not differentiable? At 0, derivative of f does not exist. F dash x equal to limit h tends to 0 of f of 0 plus h minus f of 0 divided by h. This is the f dash x at 0. Therefore, if we evaluate this limit h tends to 0 of f of 0 plus h, that means f of h, it becomes h raised to 2 by 3. H raised to 2 by 3 minus f of 0 is 0 divided by h. If you calculate this limit, it becomes limit h tends to 0, 1 upon h raised to 1 by 3, and which comes to out infinity. Therefore, f is not differentiable, and hence for this problem, Lagrange's mean value theorem is not applicable. Deduce the Lagrange's mean value theorem from Rolle's theorem. For deducing the Lagrange's mean value theorem for Rolle's theorem, we shall choose gx equal to f of x minus f of a minus a into x minus a. We shall choose this function. Gx equal to f of x minus f of a minus capital A into x minus a, where capital A is a constant and f is a continuous function in a closed interval ab, and f is a derivable function in open interval ab. Then gx is also continuous in open closed interval ab, and gx is also derivable in open interval ab. Further, g of a equal to 0, and determine a such that gb equal to f of b minus f of a minus a into b minus a, which is equal to 0. Solving, we get a equal to f of b minus f of a divided by b minus a. Thus, g satisfies all the three conditions of Rolle's theorem. G of a equal to g of b, and therefore there must exist a point c in open interval ab such that g dash c equal to 0, but g dash x equal to f dash x minus a. Therefore, g dash c equal to f dash c minus a equal to 0, and a equal to f dash c, whose value is f of b minus f of a divided by b minus a. Thus, Lagrange's mean value theorem is obtained. For deduction of Lagrange's mean value theorem from Rolle's theorem, we had choose gx function, which is nothing but f of x minus f of a minus a into x minus a. Here a is a constant term and f is a continuous function in closed interval ab, and f is derivable function in open interval ab. Then gx satisfies both the conditions, continuity and differentiability. Why ga equal to 0? Ga equal to 0 because this a minus x, we put x equal to a minus a equal to 0, and here fa minus fa becomes 0. Therefore, g of a equal to 0. And we shall determine a by choosing g of b equal to also 0. If we put g of b equal to 0, then we will get a equal to this. And if ga equal to 0, gb equal to 0, then ga equal to gb, and third condition of Rolle's theorem is satisfied. And thus all the three conditions of Rolle's theorem are satisfied. That's why g dash c must be 0, where c belongs to open interval ab. And from this we can obtain f dash c equal to f of b minus f of a divided by b minus a. Fourth example, in the mean value theorem, f of b minus f of a equal to b minus a f dash c. Determine c lying between a and b if fx equal to x into x minus 1 into x minus 2, where a equal to 0 and b equal to half. This is our problem. For solution, f of a means f of 0. If this x is 0, then this total term is 0. Therefore, f of a equal to 0. F of b is nothing but f of half. F of half equal to 3 by 8. F of b equal to 3 by 8. And f dash x equal to derivative of this x into x minus 1 into x minus 2. If we calculate this, and derivative becomes 3x square minus 6x plus 2. Therefore, f dash c equal to 3c square minus 6c plus 2. And by substituting this value in f of b minus f of a equal to b minus a into f dash c, we will get 3 by 8 minus 0 equal to 1 by 2 minus 0 into 3c square minus 6c plus 2. Therefore, we will get equation 12c square minus 24c plus 5 equal to 0. And if we solve this equation, we will get c equal to 1 plus minus 0.764, which is nothing but 1.764 or 0.236. Here, c equal to 0.236 lies in the interval 0 and half. 1.764 does not lie in the interval. Hence, value of c is 0.236. Fifth example, Calculate approximately the root of the equation x raised to 4 minus 12x plus 7 equal to 0 near 2. For solution, we shall choose fx equal to x raised to 4 minus 12x plus 7. Therefore, f dash x becomes 4x cube minus 12. Therefore, f dash x becomes 4x cube minus 12. By Lagrange's mean value theorem, f of a plus h equal to f of a plus h into f dash a plus theta h. So, h equal to minus f of a divided by f dash a equal to minus f of 2 divided by f dash 2 equal to minus 1 by 20. F of 2 is minus 1 and f dash of 2 is 20, which is nothing but 0.05. Therefore, approximate root is x equal to a plus h, that is 2 plus 0.05, that is 2.05. Applying LMV theorem again, we take h equal to fa divided by minus fa divided by f dash a equal to minus f of 2.05 divided by f dash 2.05. Minus times f of 2.05 is nothing but 0.061 and f dash 2.05 is nothing but 2.246. And if you calculate this, it becomes minus 0.0027, which is nothing but a plus h equal to 2.05 minus 0.0027, which is 2.0473. Therefore, approximate root is 2.0473. Calculate approximately fifth root of 245 by using Lagrange's mean value theorem. We have to calculate fifth root. Therefore, we shall choose x equal to fifth root of x, that is x raised to 1 by 5. Fx equal to 1 by x raised to 1 by 5 and a equal to 243 and b equal to 245. These two values we have considered. Why we have considered 243? Because 243 is nothing but fifth power of some number. Therefore, we have taken, as we are finding out fifth root, we shall take fifth power of some number which is near to 245 and it is nothing but 243. F dash x equal to 1 by 5 x raised to minus 4 by 5. By Lagrange's mean value theorem, f of a plus h equal to fa plus h into f dash c. Take c equal to 243. Therefore, f of 245 equal to f of 243, take a equal to 243 plus 245 minus 243 into f dash of 243. 245 raised to 1 by 5. This we have to calculate. Equal to 243 raised to 1 by 5 plus 2 times 1 by 5 into 243 raised to minus 4 by 5. Therefore, 243 raised to 1 by 5 is nothing but 3, because 243 is the fifth root of 3, plus 2 into 1 by 5 is 2 by 5, and 243 raised to 4 by 5 becomes 1 by 81. Becomes 1 by 81. If we calculate this 3 plus 2 by 5 into 1 by 81, we will get 3 plus 0.004938, and the final root is 3.004938. Seventh example. Verify Lagrange's mean value theorem for f of x equal to cot of pi x in the interval minus 1 by 2 to plus 1 by 2. Solution. LMVT is not valid because f is a discontinuous function and 0 belongs to minus 1 by 2 to plus 1 by 2. Cot pi x is a not continuous function. Why? At 0, the function has a discontinuity. Cot function has a discontinuity at 0 function, 0. Therefore, f is not continuous at 0 and hence Lagrange's mean value theorem is not valid. Dear friend, subscribe the channel if you have not subscribed it, and don't forget to press bell icon so that you can get the updates of the channel. Thank you. See you in next video.